Alrighty then. It says we're live. We are on multiple platforms, my friends, whether you're joining from the YouTubes, the Blue Skies, the Twitters, the Facebooks. Because what's going on? Memes here. Yes, this is a very bold claim, but we're gonna go over some very, I'm gonna say, once you notice a pattern within different things within nature, things might start making more sense. And this originally came from our something that was presented by Dr. Alexander Unzicker. So again, the links to most all this stuff is in the doobly-doo below. Feel free to verify everything I'm saying. I might just be speaking complete bunk here. But as that is simplified over here, see me at alpha equals Hbar. We'll go over that in a little bit, but let's go through a little bit of the history. So I had gone back and I looked at one of Dr. Unzicker's calculations. As we can see over here, he had an interesting relationship where if you take pi divided by 2 times the mass of the proton times the radius of the proton, you get about 3 digits and the correct magnitude and dimensions of Planck's constant, h. Cool. That's pretty nice. Now, I, of course, had to go down a Wolfram hole. Why? Because I'm a gamer. And anybody that's a gamer, if you're getting a fighting game, what's one of the first things you're going to do? Now, unless you have a guide, you're going to do down to forward, half circle, punch. Why? Hadouken! You're going to go through different iterations. And the benefits, and again, thank you to Wolfram Research for developing Wolfram Alpha, it does basically the hard stuff for you. Because the title of the stream is something along the lines of calculating the proton, electron, and neutron's attributes with Hbar and high school algebra. To be fair, Wolfram Alpha does the algebra for us. All we really need to do is look at the relationship between different stuff and things. And perhaps that might be lead to some very interesting insights. At least it was interesting for me because I was not expecting what came out. We went from about 3 significant digits for Planck's constant to about 9 significant digits for Hbar, the elementary unit of action, aka Planck's reduced constant. So from about 3 digits to 9 digits, that's about 1,000,000 times more accurate. So I think that's kind of cool. So let's go through here, and we had covered a little bit of this the other day, and upon further investigation, it seems to hold for the proton, the electron, and the neutron, and in fact, it actually gives us a little bit of a way to perhaps make some predictions, because it seems to line up, and the interesting thing is it looks like the neutron might actually be a wee bit smaller than the proton, according to these calculations. And again, this is conjecture. We're going to have to follow the experimental evidence. Why? Well, we need to ground ourselves in reality. It's like we can have all the fancy predictions, the most beautiful mathematics in the world, but if it isn't really doing anything for us and we can't really connect it to experiment, ultimately we want to be able to do something with it. And basically the whole goal of this is if we increase our precision, what can we do with better precision? It's kind of like, well, rough estimate for pi is 3. Okay. 3.14. Okay. 3.14159. That's going to be good for a lot of engineering things. But if you're trying to do extremely high precision engineering, you're going to want those extra significant digits. Okay. So let's stop bloviating and let's actually get right into it. So let's bring up Dr. Unzicker's original video. Let me just go over here. Okay. Oh God, I brought up like everything else except the initial video I'm supposed to be going to. I apologize. All right. So we got let me just search Proton. Okay. So an intriguing coincidence. So let's bring this up. Okay. So share with the class here. All right. And again, the link is in the doobly-doo for anybody that is interested here. All right. So what do we have? We have, let me make sure I actually am sharing the correct thing. Tab, Proton Radius Riddle. Okay. And again, this is from about 7 months ago from Unzickers Real Physics. Again, do I agree with Dr. Unzicker on everything? No. But then again, I don't agree with anybody on everything, including myself. I can change my mind. Okay. Let's see what the good doctor is saying.
Is a coincidence. And this is very interesting. It has been noted by a couple of heterodox scientists, interestingly. And I mean, two things to mention here. Why did I insert this p over 2? Because
pi over 2. That's essentially what he's saying there, because you could pronounce pi, p, whatever. I understand what he's saying. So basically the claim is, this is all we really need here, is the approximate value of Planck's constant is about equal to pi divided by 2 times c, the speed of light, times the mass of the proton, times the radius of the proton. Cool. All right, so we don't need that. So let's actually go to it to where I actually have some tabs set up for this. So let's get nerdy, everybody. All right, so now we can do the window. All right, here we go. Okay, so Dr. Unzicker is saying, he's pointing out, and again, other folks have pointed this out, that if you take this following expression, basically pi divided by 2 times c, the speed of light, times the proton mass, times times the proton radius. Now, note, this is something that Wolfram Alpha helped me, because, see, we have an option up here. It says, assuming the proton mean square charge radius. Okay, that's generally what we refer to as the radius of the proton. And there was a big thing where we thought it was about like 8.7 or so femtometers, or 10 to the minus 16, whatever magnitude that comes out to be. And apparently some more recent measurements seem to disagree with that long-held thing, and we had some confirmation, and ultimately it looked like the proton radius was a bit smaller, by about like 3 or 4%. That doesn't sound like much, but if you're talking it's like 16 significant, it ends up being pretty big difference. Okay, so as we can see here, when we put that all in, we get about Planck's constant, h. Okay, so we get the first couple of digits over there. All right, that's really cool. And again, it's pretty close to Planck's reduced constant. It's about 2 pi off, because that's the difference between Planck's constant and Planck's reduced constant. Cool. All right. So let's see, where do we go from here? Okay. So seeing that, I'm like, of course I had to go down a Wolfram hole. So what do? First off, one of the things I learned from that, let's just look at the dimensional components. So let's just take off that dimensionless pi divided by 2, because that's a modifying term. Okay, so again, in Wolfram Alpha, we need to clarify. It's saying, oh, C, the charm quark? No, we want to use C as in the speed of light, a unit. Okay, and we're doing multiplication. So we do this. It's like, all right, that's pretty cool there. So one of the things that I noticed is it gives us an option here, assuming the proton root mean square charge radius, whatever that is. Wait a second, there's an option. We can use the classical radius instead. So basically that's just assuming spherical things there and everything. So what happens if we click this? Okay. So let's go through. So we've got our same thing, except we took off that pi divided by 2 dimensionless modification term, and we have c, the speed of light in a vacuum, times the proton mass, times the proton's classical radius. Okay, what does it give us? Gives us these numbers. Those numbers don't mean a thing to me. Now, what caught my eye is, wait a second, it's about 137th the value of the reduced Planck's constant. For those of you that have been catching up with some physics and or pop sci, you may have heard that whole 1 over 137. Like even in, was it Rick and Morty, Rick Sanchez, the primary one, is from universe 137. Ah, see, pop sci references and everything there. So that got my noggin a jogging because it's about 1 over the fine structure constant. So of course, we had to play. So we go over here. So we take that whole thing. We're taking the speed of light, the mass of the proton, and then we're taking the proton's classical radius, and we're just dividing this whole thing by the fine structure constant. And then we get these numbers here, which, oh, looky. This seems to be about the first 9 significant digits. Planck's constant is defined at 10, so the last digit here should be 17, but the speed of light only has 9 digits going in. So it seems to be rounding up, so it seems to have about 1,000,000 times more agreement if we rephrase it in the form of Planck's reduced constant, Hbar, rather than Planck's constant. I think that's pretty neat. But wait, there's more. So of course, if this happened to work for the proton, that raises the very next question. Is this just a coincidence? Or might it be trying to tell us something? Might there be something interesting going on here? So, we did the calculation for the electron. So again, we're doing the same thing here. We're taking the mass of the electron times the electron's classical radius times the speed of light divided by alpha, the fine structure constant. Looky, these numbers look very similar. Oh, this, again, seems to be the same numbers. Huh, I was not expecting this at all. So it does seem to hold there. And, oh yes, welcome, Rick. One of my teachers here is in the chat. It's good to see you. I hope you are recovering, my friend. I look forward to seeing you in the future and having more discussions because I've learned a lot. You are definitely, between you and Stephen Wolfram, you're basically the folks that helped give me the actual gumption to actually come out and become a monk at the physics monastery. So thank you. This literally wouldn't be possible without a extremely low probabilistic series of events. So I thought this was pretty cool. So let's continue. Okay, so if this simple expression, I claim, happens to hold for the proton and the electron, well, that leads to the next question. What happens if we do it for the neutron? So I tried, and let's do this. We'll duplicate this tab, and then let's just replace a couple of things. There's a little bit of a twist here, because if we try to do this for the neutron, so the neutron mass, which we do have, it's a little bit more massive than the proton. And then let's try the neutron. I don't think it really has a class. Long story short is we don't have enough data. I believe right now we have the neutron to about neutron's radius to about 0 significant digits. We might have its Compton wavelength, but ultimately we don't have enough. So I'm like, oh, what can we do? So what I did was I applied the awesomeness of algebra. What the heck am I talking about? What am I talking about is, well, if we claim that this should hold for the neutron as well, all we did is, we know the neutron mass about 10, 12 significant digits-ish. Well, if we assume this hold and it should equal h bar, well, we can solve for x. So I literally just put in x meters. Oh God, I can't even spell the neutron right. Wow, it's a good thing Wolfram Alpha carries me. Okay, so we get this number for the classical radius of the neutron. Okay, so we took that and we just plug it back into our expression. So we're taking the speed of light times the mass of the neutron times this estimated classical radius of the neutron divided by the fine structure constant. Oh, and looky. Of course we're going to get the same thing because we literally set it equal to that. Now, this classical radius is interesting because number one, it's a little bit smaller than the proton's classical radius. And you're like, wait, the neutron is heavier. Shouldn't it be bigger? Some people speculate that it is, but if we're going to take what we've learned from some astronomers and cosmologists, it's like, well, once you start getting to a neutron star, the more mass you add, the smaller it gets. That does seem to hold up here. So, hey, Jedi. Good to see you, my friend. Good to see you. Listen, I'm just providing a little bit of something that I found. And full disclosure, we need to give credit where credit is due. Upon doing some of these calculations for, especially I think it was the radius of the proton, because that's the interesting thing, because there's a way to go back and forth between this. Did I have this next? Okay. So which one was this? Okay, so this is when you divide by 1/4 alpha for the proton and neutron, it does seem to give you the RMS, or the root mean square radius there. Okay, so this is for the neutron, which is interesting because it's a wee bit smaller than the proton radius that we can calculate, which, let's see, where is this? I gotta go through it. Okay, so this is basically applying the same thing. So this is the mass of the proton in kilograms. This is the speed of light in meters per second. And then we're solving for x, because Hbar is the elementary unit of action. Its dimensions are mass times an area divided by time. So we got mass, we have length squared, which will literally give us an area, and then divided by a time, which will give us a mass area rate, aka the units of action. Okay, so when we do that, we get this number out here, that 8.4123, yada, yada, yada. So coincidentally, if we go to, what was it? Hold on, I got, let's bring up code data, proton radius. All right. So as we can see, the proton RMS charge radius, so the root mean square. This used to be about 8.7 or so. The more recent measurements seem to put it at about 8.40, and then we got pretty big error up here. So that means these last two digits, we could either add that 64 to bring that up to a 1 and something, or subtract it. So that would go down to about a 40. So at least we're in the error bars there. And where was this? Let's see. There's that. Okay, so that's for the neutron. Okay, so this is the estimating for the neutron, and then this is the estimated neutron radius at 8.400. And then when we're this guy, this is the proton radius, 8.41. Huh. That seems to be a little bit larger than the neutron, but okay. Long story short, and bloviating is I didn't invent this. I'm not the first person that did this. So what I did is I literally took this string of digits, I threw it into Google, I searched. I found two papers that seem to have come up with at least this similar results. And let's go to those over. Oh, I need to do a new window. Pardon. So let's go to, it should be this guy over here, I believe. Yep. All right. So the first, this one was from an Israel Freed. I'd sent them an email. According to the bio that I had tracked down from an old tripod site to find the email, I'm not sure if this gentleman is still with us. If he is in his 80s. But he had similar things. Now, again, he framed it a little bit differently. I think the claim was originally that the proton and the neutron had the same radius. Okay, so a little bit different, but I did find similar results. So I think, where is it? He ends up going into it at some point. The link is in the doobly-doo below. And then the other paper that I found these digits was from actually the Hyama Natural Science Research Institute from Tokyo, Japan. I actually need to send them an email as well to let them know, because they basically came out with something like this. I think this is one of the more recent measurements when we had that conflicting data there. Okay, so these are in the doobly-doo below. Feel free to check them out. I just want to give credit where credit is due. I wasn't the first one to come up with this. I found a couple of papers. I think one of them had like no downloads, and then the other maybe like one, barely any engagement. This one is on Vixra. The other one is in a preprint via, was it either one of those IOP Psi things, or I found the ORCID ID and stuff. So I had logged in and tried to see. But some people can be hard to reach. But just want to give credit where credit is due, because that's important. Okay, so let's rock that down. But, well, see, that's the thing. Every once in a while, I know Rick has told some of these stories for some of his research where you do a calculation, and you're like, that's not supposed to be there. What's going on? As soon as I ripped off those dimensions, and I'm like, it's about 1 over 137. I'm like, okay, maybe that's just a coincidence. Put it in, and then all of a sudden it's like, oh, look, 9 digits of accuracy. It's like, I was not expecting it to work that well, but maybe this is telling us something. If, when we're taking the speed of light in a vacuum, we're multiplying it by a particular particle as we know it, because maybe particles aren't even necessarily the best concept. But if we're taking the speed of light, multiplying it by a particle's mass, and then multiplying it by its radius, well, the speed of light is length divided by, oh, here, this is why we have a whiteboard, okay. So if c, the speed of light, is equal to, basically, it's the minimum of length, so L sub p, the Planck length, divided by T sub p, the Planck time. All right, that's a dimension of length, that's a dimension of time. All right, if we're going to do m sub, I'm going to do plus for the proton. That's a dimension of kilograms, kg, and then we're adding in another m sub, I'm going to do rc, just for classical radius, and that's a dimension of meters. All of a sudden it's like, all right, we're going to get an expression that's going to be kilogram, kg, so a mass times a dimension of meters squared, and then divided by the dimension of seconds. All right, there's our unit of action. So that's why when you have something like that, that's interesting. And then it's like, all right, well, what do we need to divide it by? And if it happens to come out to be something like, that seems to be very important within physics, like alpha, aka the fine structure constant, that seems really neat. Oh God, my head is in the way because it's so fat, sorry. But, okay, let's go back over here. So let's bring up this other guy. So what are we doing? So basically the whole claim is, back to this window, is if there is some there, and at least upon initial calculations, it does appear to be that there might be something very interesting going on here, we should be able to do some algebra, or at least let Wolfram Alpha do the algebra for us, and be able to go back and forth for these things. So if we had that, so let's take, remove the proton mass. Let's just put x kg for kilograms there. And then we're going to set this equal to Hbar, the elementary unit of action. Okay. We're going to need to use the classical radius here, and we'll go over. There's an interesting conversion factor that I'm not sure why it works. It just seems to work. We'll go over that shortly. Okay. So that should give it. Oh God, I did something totally wrong. Oh, I forgot my own dang convention. We got to divide it by the fine structure. You can write alpha, but every once in a while it'll think you're talking about the alpha Feigenbaum constant. So Structure constant. Okay. See, I used to make these mistakes, and I would lose my mind because I was literally just copying that, but I didn't have an intuition for what was going on. So I'd be like, why am I off by like 76 orders of magnitude? And it's like, oh, wait. I used the Planck temperature instead of the Planck time. So not only am I in the wrong dimension, I'm off by 76 orders of magnitude because the Planck time's at about 10 to the minus 44. The Planck temperature, big T sub P, is 10 to the 32. So bada boom, bada bang, 44, 32. There's your 76 orders of magnitude. All right. So let's see. Classical radius. There we go. All right. So this should give us, oh, looky. We're solving for kilograms. Let's open it up. So let's throw our little dimension of measure there. Kilograms. Oh, that seems to be really dang close to the mass of the proton. I mean it. 1.67, 1.67, 26, 262,193. Okay, it's the mass of the proton to at least all the known significant digits. That might be like a 26 or something in there because it's rounding. But that's really interesting. I was not expecting this at all. And like, to be fair, when I got this, I'm like, all right, this has got to be something trivial. It's like, people have to have known this. And then when I do a search for at least a string of like 8, 9 significant digits, I'm like, I found like those 2 papers. They're not published in any major journals. They're, I think, 1 or 2. Yeah, actually, they're both on preprint servers. So I'm like, and they seem to have no interaction. One was done by a dude that I'm not even sure if he's still on this mortal coil. I haven't gotten a response yet. But it's like, okay, well, maybe this may be a bit of an argument for perhaps there are folks outside of the standard academia realms that have interesting things to say. All I know is I at least got one wow from somebody within the Wolfram Institute, so that was encouraging, especially when they happened to have studied, I believe, particle physics and stuff, and I'm like, okay, I was just thinking, I'm like, oh, no, this is covered here. I asked Thad, I'm like, Thad, do you remember any of this stuff from school or quantum mechanics? He's like, no, I don't remember any of this at all. So it's like, okay, maybe this is a relationship that hasn't been explored as much as it should. So it's just, again, just kind of spitballing here, and all it comes from is just our simple little expression, assuming that, well, maybe is some coherence in nature. Maybe we've actually really done a pretty dang good job of sciencing things. We figured out a lot of stuff, and now that we've literally have millennia of human knowledge and measurements, and if we happen to have tools like a computational calculator that happens to have probably one of the largest databases of units in the world, it's somebody had asked me, it's like, well, how did you come to this convention? I'm like, I didn't do it. I'm like, literally, I put the things into Wolfram, and like Wolfram Alpha told me. It's like, oh, look, 1 over 137. It's like, no, it can't be. And then it's like, it seems to have very good agreement. And I'm like, huh, that's very, very fascinating. Let's see. Well, Jedi is commenting that they're more of a language history buff. The stuff is amazing because of where I live. It's quantum mechanics quantum mechanics is mind blowing, but it's like, if there is some there, and again, we're conjecturing here. Again, the data seems to line up to have really good agreement. And the only reason I did this is because of the internet. Because actually, if anything, I was trying to make Thad feel better, because Thad and I were going to the Vistify Psi conference in Sembra, Portugal in a couple of weeks here. And Thad had come down, I think he had seen something from Unzicker where he was covering like the variable speed of light. He's like, oh, is he a variable speed of light? Because Dad happens to have his own beliefs and thoughts on that and everything. So I'm like, no, he just seems to be entertaining ideas from my knowledge base. So if the knowledge happens to be able to lead us to a better understanding about what's going on in our world, then maybe we can do better things. I don't know. Maybe we can actually try to explore the cosmos and actually like go through and just explore the heavens, if you would, there. Because, well, if we can do better science, again, just strictly from a perspective as somebody that personally for me, one of my longest held titles is gamer as a personal identity. So if I see something interesting, I'm going to do all these random things to it. And if all of a sudden Wolfram Alpha is like, oh, it's half this, I'm like, all right, well, let me divide by 2. If it says it's about 137th of it, I'm like, well, let me divide by alpha. Why? Because I can. And the sheer fact that you don't need to put in all the little digits and everything, ultimately you're going to want to put in more digits to verify to the maximum precision. But just as an initial calculation tool, I remember when Thad was saying, he was highly suggesting, if you have a question and you can frame it in the right way, very often you can ask Wolfram Alpha. And now we have these large language models, and a lot of them, actually, if they're going to do an actual good calculation, very often they're sending an inquiry to Wolfram Alpha. So partially, I'm like, I think that might be why some of the servers are lagging at some of the times where I'm trying to do a calculation here, and it's like the LLMs are probably querying Wolfram Alpha and slowing it down a little bit. But as Professor Wolfram had said, one of the biggest new clients that they have are actual large language models as well. So I just think that's really cool that if you could have a simple, and I think this is where, I know Dr. Hassenfelder, she very often will say, it's like, yes, people obsess over beauty and equations and stuff, but it's like, okay, I think the whole thing is, it's beauty or simplicity. So if you can have the most simple expression or a minimally necessary expression to maximally describe what is going on, well, isn't that what science is supposed to be? Because otherwise, you can always add in different epicycles and stuff. It's kind of like for the planets. Initially, we were talking about like epicycles and stuff. It's like, well, if we're assuming everything is going around the sun in a perfect circle, it's, well, how do we account for this stuff? Okay, well, it's going in an epicycle. It's having like another loop there. Okay, that works well. But then if you need to add more loops and more loops and more loops, does it have the same explanatory power? And again, it's like, what is it? The retrograde of Mercury and stuff. Because, well, it seemed to not work. Like, big G, like Newtonian gravitational dynamics seemed to break down for Mercury. Why? Well, personally, we needed higher precision. Because if there's one thing we've learned from Professor Penrose, it's, well, let's actually just play the clip. That's probably better here. So, since we actually have it, don't believe me, believe an actual expert in general relativity. Penrose. Okay, so let's stop sharing this. Let's present over here with the class. Go to the right tab. Okay. So this was a clip that took us at least a couple of years to find. Thad remembered hearing it. He thought it was with Professor Green, but it's actually Professor Penrose. So it's titled Professor Roger Penrose on Newton and Einstein's Precision on Gravity. So let's go right here.
Now, mathematics can also describe things in the ordinary physical world, gravitational attraction, electromagnetic attraction, and with the same kind of descriptive accuracy?
Well, there's another, yeah, even more in a certain sense. Newton's theory already had a precision of something like 1 part in 10 to the 7, so that's 10 million.
Wow.
And then Einstein comes along and produces a theory which is now known to have a precision something like 10 to the power 14.
So what does that now begin to tell us about what mathematics really is?
Yes, well, in a sense, this is telling us that our picture of physical reality depends on something, in a sense, which is more precise at least in our understanding of it, than how we think about the world. It has its own life, in a sense.
All right, so again, I'm showing that because it does also help bolster my, or at least what I've learned from Thad, as well as a bunch of other folks, the general hypothesis and intuition. It's like, all right, well, if Newtonian gravity goes for about 7 digits of precision, and then Einstein comes along and we get 7 more digits of precision, it's like, well, maybe because of how massive the sun is and how close Mercury is and how small it is, maybe we need a little bit more than 7 digits of precision. Coincidentally, I believe it was Lord Kelvin that's attributed with saying that, oh, most of physics has been settled right now, and it's only a matter of determining the measurement of the 6th significant digit. Okay. Now, right around the 7th significant digit, things started to kind of get wonky there, and then we needed to develop further things, such as quantum mechanics, to help us figure out predictions and stuff that seems to be going on. Now, again, a lot of times if you're going to present something, and especially if you have a calculation, not always, but occasionally you'll have some folks say, it's like, oh, what do you think, you're smarter than Einstein, the de facto dude that's a genius and stuff? It's like, well, if Einstein didn't finish his quest, isn't it up to us to work harder to complete the good professor's goal of trying to help unify a theoretical framework to help better describe what's going on? And the sheer fact that we have Einstein's works, we have Planck's works, Maxwell's works and everything, and we, as far as I know, and again, I am not a traditionally trained physicist or anything. If anything, I'm basically just, I'm a numerologist I'm a monkey with a magic typewriter and an idea of where to look based upon what folks have shared with me. So whether it's somebody I've talked to on here, whether it's somebody I've talked to in person at the monastery, people I've visited on different trips, had discussions on Discord, Twitter, behind the scenes conversations and everything, a lot of it I just don't know any better. I haven't had anybody tell me no, or where to go, or say I'm only okay, you don't want me to sing here. But welcome, Poindexter. Good to see you, my friend. We're just doing a whole bunch of blasphemy here right now. Oh, that's right. Oh, you're down by Cape Canaveral. You're gonna see the launches and everything. Okay. Next time I'm in the greater Florida region around those parts, I'm gonna have to hit you up, and because I've never actually seen a launch. Okay, I may have been down in Florida when there was a launch, but I think we were in the Palm Beach area, and I think we watched it on TV because it was a better view rather than trying to look off in the disc. But no, if you're right down there, dude, I am very jealous. That's really, hey, listen. That's fine. You arrive precisely when you were meant to be. That's the thing. Listen, when people actually talk about quote unquote a theory of everything, I use the quotations there because very often, if you're trying to explain everything, that means you gotta explain everything. And consciousness and stuff, that seems very hard. For me, I've become less ambitious. It's like I'm looking for a coherent theoretical framework to try to figure out about what's going on. And again, these are little things here where even if you toss it into ChatGPT real quick, it's like, this seems to be very remarkable, but there doesn't seem to necessarily exist a framework utilizing this particular thing. But it's like, does it really surprise anybody that, well, if you take something important like the speed of light, you take an attribute of an elementary of a particle, because as far as we know, the electron is an elementary particle. The proton and neutron do seem to be composites of something. All right, so if you happen to take the speed of light, the mass of a particle, and the radius of a particle, and you can divide it by a dimensionless constant that seems to be really dang important, like the fine structure constant, and you get about 9 or so digits agreement with the elementary unit of action. It's like, I looked at that, I'm like, all right, well, that's surprising. I'm like, well, people have to know this. And then all of a sudden it's like you show it to somebody that's actually studied particle physics and stuff, and they're like, wow. It's like, I was waiting for, oh no, that's covered in like day one or something like that in quantum mechanics. It's like, again, I don't know any better. I'm letting Wolfram Alpha basically guide me. Because it's like, if you're playing a game, because that's how I view it there. Because a lot of times, at least in college, I like to go down wiki holes with friends. One of my friends, he was a chemical engineer. And we would go down these things and we'd see all these great things about graphene and everything in the future. And I think, God, going down those things, and now we're seeing that twisted multi-layer graphene, coincidentally twisted at the magic angle, seems to exhibit some superconducting properties. That's really encouraging, because if we can figure out fusion technology, because that's the big thing, because then we could have clean, more or less for humanity, unlimited energy. And then if you have superconductivity, so you can actually transfer that energy basically with minimal if any loss, and you could go even further from that, and we could actually, perhaps Thad's ultimate goal is if we could actually have 5D printers. What's that? Because we have three-dimensional printers right now, 3D printers, so we can do some things. But if we could also do some manipulations of the 5 platonic dimensions, I claim, which are time, space, charge, mass, and temperature. If we can manipulate those things, number one, we can get the constants of nature. Okay. And if we could do that on a good enough, high enough precision, which is why precision's important, well, what's to stop us from, all right, well, stand the best tomato in the world, get all the information, and ultimately we could be in actual, like, true post-scarcity at some point. And again, it's going to be a long road to get there, and we will remember the powerful individuals in positions of power and corporate entities that did help get us there. So I believe there would be a lot of goodwill, because ultimately, well, if we have true post-scarcity, then we get rid of a lot of the reasons to fight each other. And if people still want to fight, we can legalize dueling. That's always a potential option here. And again, the means of destruction channel does not promote violence unless we were to legalize dueling. I think we should let consensual adults engage in what consensual adults would like to do. Again, personally, I don't think most folks would actually like to duel, but if folks really want to do it, hey, I ain't your dad. But you watch it from your driver 2 days until flight 9. Dang. Oh, the lagoon. The lagoon. Oh, I've heard such, I think I've seen pictures and everything there. Oh, very nice. I need to go back to Florida. I haven't been there since 2020. Early times. Yes, I took a picture of a Corona girl that was doing a promo and everything. I'm like, wait, hold on. You're giving the Coronas, and that was right when they were declaring states of emergency and everything. Different time, but all I know is, hey, a lot of people were hurting. We lost a lot of folks. But at least for me, there were a lot of educators, whether it's Professor Keating, Professor Carroll, a lot of folks going onto the internet and sharing education. Like Professor Wolfram started doing his science and technology Q&As and everything there. And it's like, wait a second. It's like, whether you agree with Stephen Wolfram's general outlook on things or not, it's like he is a pretty eminent scientist. So even if some folks, the criticism was, it's like, oh, Stephen Wolfram, oh, he hasn't published anything in like 20 or 30 years. It's like, really? So what you're saying is your gauge of somebody knowing what might be going on is based upon your H index. Okay. Well, listen, hey, there's plenty of parameters, and you can use all those statistics and everything. But as far as I understand, Stephen Wolfram's explanation is like, yeah, publishing papers and stuff is kind of a pain in the butt. So he's Stephen Wolfram. He has resources. He's got enough street cred anyway. He just puts it onto his blog. And then he'll do a live stream and stuff about it. And occasionally people will take that. And then actually I've seen probably published on maybe the archive for him and stuff. But that's the thing. We never know where a good idea may come from. This was literally just me like, oh, here's an interesting, fairly, I would say, beautiful calculation here. It's like, all right, if you have something where, and again, we got some symbols here. Oh God, I forgot C. God, fake science. Fake science, bad memes. All right, boom. There we go. I'm realizing after the fact. Okay. So where should we go? Oh. Okay. So I don't know about you all, but when I was going through the United States education system, I am a state-educated individual. So they used to have little sayings and stuff to help you remember things. One of the things that I remember was my very educated mother just showed us 9 planets, which was basically to help us remember the 9 planets. I'm still going to use that. Pluto might be a dwarf planet, technically, and again, if we're going to be technical, okay, maybe it doesn't qualify as planet, but I'm still going to say it, even if I need to drop the P at the end there, because it helps you remember something. So Thad did some magical algebra, and let's go over here. So if we take a look at this guy, Thad just did some standard calculations and everything, and he's like, I have a prediction. He's like, type this into Wolfram Alpha. What is this? C me at alpha equals H bar. C me at alpha equals H bar. Okay. What does it actually say? C, it's the speed of light in a vacuum, even if there is no true vacuum. Okay. Me is the mass of the electron. At, it's A sub naught, so A0. Basically, it's the Bohr radius of the electron, times alpha, the fine structure constant, equals H bar. Okay, so that's where we get the C me at alpha equals H bar. So let's, and again, feel free to trust but verify. Actually, if anything, don't trust me. Don't trust me. That's the thing, because a lot of times I see something, I'm like, nah, there's no way this could actually be something there, because most things are wrong. So every once in a while, if you happen to find something, you're like, okay, well, somebody obviously did that before. And to be fair, it would not surprise me at all if a lot of this stuff, some physicist or student or something, somebody probably noticed over the years, and they just probably thought it was trivial. It just happened, because that happens with mathematics and stuff. You'll go through like somebody's old journal from like a few hundred years ago. It's like, wait a second. They wrote this down like 50 years before any of this was published. And one mathematician was like, oh, isn't that obvious? What might be obvious to one person may not be obvious to everyone else, because we're all different. We all have our own unique life experiences. So let's go back over here. So let's do our little, okay. Let's go to this guy. Let's do one more. We'll get to that in a second. Okay. So let's do our C me at alpha. So we're going to do C, mass of, all right, electron mass, and then that at is actually the Bohr radius, and then alpha. We're probably going to have to adjust this. Okay. So we're going to change alpha to the unit rather than the alpha Feigenbaum structure. Okay. So as we can see here, we have our expression, our C me at alpha. Da-da-da. Oh, look. It seems to come out to that same number that we're generating. Huh. I think that's pretty neat. And again, it's in the right dimensions. It's of the right magnitude and everything. Let's do this. Let's divide it by H bar. Might need to redo. Hold on. Let's change this to the fine structure. Fine structure constant. There we go. Oh, multiplication. Huh. Well, if you got a thing and you divide it by another thing and you come out with 1, that might be encouraging. I'm just saying, listen, this is a conjecture here, and again, there seems to be very little literature on this. Like I said, I literally needed to take, what was it, one of these, where is it? This guy here. What's it? Yeah, I literally needed to take this guy here, just copy paste, and I think, what was it? We literally just went to Google, and it's like, okay, that gives nothing. All right, so let's take this off. Let's literally just take this string of digits. Okay, nothing. Let's take off a digit. Okay, so this is how I found that article from Mr. Freed. And then, let's go back. I think there's a 0 after this, and I think that's how I found, okay. Oh, jeez, there's like nothing there. This, yes. Repeat with omitted results. So, yeah, this is basically all for like the same article. Or he had a couple of versions he withdrew and then did some updated ones, but okay. So out of at least the entire internet that's at least Google has listed here, for at least all of Google searching for this number, we have 1, 2, 3, 4, 5, 6, 7 results. This is for something about a map. This is another map thing that looks like a fastener for some mechanical thing. This is basically from the same dude. This is from the same dude. This is from the same dude. This is from the same dude. Okay. Again, I thought it was interesting, but that's one of the reasons why we do have that peer review thing, because you want other experts to take a look at something. And then again, maybe there's a fatal flaw. Maybe it doesn't make any sense for me to be doing this at all. I mean, maybe it doesn't, but at least for me personally, this is personally kind of satisfying. Because it's like, at least for me, and regardless of whether anybody else wants to pay attention to this at all, it gives me a better intuition for what might be going on within our realm of persistence. Now, will we persist forever? I have no idea. I mean, I can conjecture about different things. I'm going to be presenting a particular little model in Portugal for a conjectured mechanism of dark energy. Now, maybe dark energy is, or whatever we assume might be dark energy, maybe that's just an observational effect, because if you take the general magnitude of the cosmological constant, it gives you like inverse meter squared. Okay, well, basically if you take the square root of it and everything, you get about the radius of the observable universe. So you're like, is this just an observational thing? And even if I'm conjecturing that, and even if I have a pretty equation that seems to match a lot of the cosmic microwave backgrounds, calculation for the cosmological constant, seems to have pretty good agreement. Would I love for it to be true? Sure, but I got to be open about that it doesn't necessarily even jive with what I'm saying is a physical mechanism now. Now, to be fair, if you do include some angular rotation there, at least according to the Royal Astronomical Society, you can actually seemingly account and get rid of the Hubble tension with that. Now, is that the answer? I don't know. Again, the way that science typically works is, as we make scientific advances, we can engineer cooler and cooler stuff. And as we engineer cooler and cooler stuff, we'll end up getting we'll get better precision, so we can take even more accurate measurements, and then be able to extend our science to the next level, and so on and so forth. Now, that's at least how it works in most strategy games and stuff. So whether it's Total Annihilation, I like the Kingdoms version and stuff there. But when you invest in science and technology, you're going to develop better things. That's going to allow you to do more stuff, and you're going to be able to continue to grow and flourish, and also be able to defend yourself. And whatever your goal within that game, whether it's literally to annihilate your opponent or to, I don't know, build a thriving community, kind of like what I did back in Ark Survival Evolved, because a lot of those survival games, what do? They plop you down in somewhere, and then all of a sudden it's like, oh, what do you gotta do? You gotta go punch a tree. Why? Because that's how you harvest wood in that game. Whether it's Minecraft or something, and then you pick up some stones and thatch, you make your little axe head, and then you can start to mine blocks and trees and wood and develop shelter, because if you go to sleep in Minecraft and you don't have shelter, you're probably going to get eaten by a zombie or something like that. That's just the standard framework for gaming, and if apparently within Minecraft you can actually build a computer, I have no idea how that actually works in anything, but wait, if you're able to build something potentially Turing complete within a simulated world, and we can build things as far as we know are Turing complete, that raises a whole lot of questions. Now, I'm not saying I have the answers or anything. I'm basically just kind of a numerologist that, like, looks at stuff, plays around from a gaming perspective, and that, okay, well, how does this relate to this? How does this relate to that? Okay, that's cool. And we're looking for coinkydinks or coincidences there. And when you find some coincidences, and again, I had no reason to look for this, except that I was actually trying to make Thad feel better about perhaps Dr. Unzickers' perspectives. I'm like, no, look, he's looking at this. This has 3 digits of precision. I'm pretty sure you'd be interested in the hyperbolic partition equation, aka this dude. When you, we need a, this guy, yes. We need the new charts actually have the absolute magnitude brackets there. So basically, we're just taking the magnitude of that number there. But this happens to be, again, I would claim a fairly simple, I would posit beautiful expression that seems to get the fine structure constant, or at least its amplitude, to all the known digits. Now we can argue around the 10th decimal place or so, and again, maybe past that decimal place, it loses accuracy. Okay, maybe this expression does need a modification. And to be fair, at least according to the current measurements, if you just divide this magnitude by √2, which apparently seems to be important within quantum mechanics, you eerily get like right in the error bars for the current measurements. So see, that's the thing, because a lot of times there's this thing called red teaming. Like, if you get a cool calculation or something, it's like, okay, how are people going to nitpick it? Because you always need to put yourself in the perspective that people are going to criticize things. Why? Because that's just the nature of humanity. We love to criticize things. I love criticizing things. But that's one of the things. So if we criticize ourselves first and bring up people's objections, it's like, well, we're going to need to work to overcome those objections, because that's sales 101, or at least from when I did corporate sales and stuff. They're literally entire like training manuals about overcoming customer objections. And a lot of times it's with a script and you go through this. And see, I always prefer just learning stuff about the products. Learn stuff about the products, talk to people, and figure out what's important to them and relate it to them. Because at that point, now you're actually being a sales professional, rather than I'm just saying whatever I can to secure the sale. Why? It's because in people's self-interest. If you're in your self-interest to sell this product for as much as possible, why? Your commission check's going to be larger. And if that's the only thing that's driving you, well, you might not always be providing the best value. Now, I'm not going to really hate on somebody for making an honest living, but personally, just that's one of the reasons I kind of got out of sales. I was okay. I really wasn't even a good salesperson. I was just kind of good at dealing with people, I think. So that's my personal opinion. Are we all imagination? A prompt of an AI? Are of us? I can't say. I ain't no god nor prophet. I'm just a dude on the internet that's interested in scientific stuff and things, and I just thought this was at least worthwhile sharing with some folks and kind of getting that stuff out there. And I realize I love investigating things. I love going down holes. I love having conversations about this stuff. Because again, you never know where a good idea may come from. And maybe it's an idea that, maybe that idea maybe doesn't necessarily quite have the substance that maybe what somebody might be intuiting, but somebody else might look at that and be like, okay, that's not exactly what I'm looking for, but it helped me just reconfigure something in my head that helped me understand something else. So that's one of the reasons why I'm sharing, because if this helps somebody else figure out stuff and we can actually help, I don't know, maybe help level up humanity a bit, I think that would be a better world. So that's about all I got for right now. So put in the requisite hours. So, hey, thank you all for watching. Those who have joined us now from all across the internet, and those who may temporarily join us in the future. It's a wacky and wild world out there, but it's open for a better tomorrow. Peace out, everybody.